Hi, my name is Brendan Casbolt, and today I'm going to be presenting a question from my master's assignment. Okay, so let's get started. Okay, so the question is, we have n independent random variables from a distribution with mean mu and variance sigma squared. You let S squared be the usual unbiased estimator of sigma squared. So part A shows that for any estimator, show that for any estimator of the form AS squared, where A is constant, the mean squared error of AS squared is going to be this. So let's have a look at the solution. So the first step is pretty easy. We just basically expand what's in the brackets. Next, we just separate each term according to an expression in terms of expected values. And in this line, what we do is we express ES to the power of 4 in terms of the variance of S squared and the expected value of S squared all squared. Now, we know that S squared is an unbiased estimator. So this means that ES squared is just going to be basically the variance, because S squared is an estimator of the variance. So our term in the third line, A squared, ES squared, all squared, reduces down to A squared similar to the fourth. And finally, what we can do is we can just combine all the last three terms and rewrite it in the form of a square, and we get our final result, and then we're done. So let's have a look at the next part. So part B says show the variance of S squared is equal to this, where kappa is going to be our kurtosis. So this question is a little bit difficult. It requires us to prove basically from scratch. We're starting from the definition of our sample variance, except we're going to be expressing our sample variance in a different form. So the form we're going to express our sample variance in is this form instead. And then we take the variance of both sides. So taking the variance of both sides, we obtain this. And our next step, we can take out 1 on n minus 1 and square it because of the variance. And then we have a sum of variances of sums, basically, plus the covariances of each sum. So we're going to end up having n minus 1 by n minus 2, lots of covariances in this case here. Also, I've set SI equal to the sums within the variance. Also, another property that comes in handy is our expected value of our sums, which is actually equal to 0, which you can see a little proof over here. Okay, so let's move on. Okay, next we're going to be evaluating each part of our variance basically in different sections, because they are quite time consuming. So we're going to start with the covariance of SISK. So basically we just start with the basic formula for the covariance, which is this given here. And we know that our expected values of SI are 0. So our covariance reduces down to this form here. Now this bit's interesting because if you think of it, if you ever look at the terms inside the sums, if we were to expand everything out, if xi minus xj all squared was completely different to xk minus xj all squared, or in other words, completely independent of xi minus xj all squared, then for this to happen, then when you think of it, our xj's have to be different, completely different, right? And we also know that our expected values of each of these terms are 0. So if they're independent, then we can split it up into two separate expectations and multiply together, and we get 0. So we have this little trick where we take out the terms that are actually dependent. So if you have a look at the third line, what I've done is I've taken out the terms that are dependent, and I've added the extra terms on, because they're not necessary, because they eventually what will happen is when we separate the terms in terms of expectations, that plus dot 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 bit will equal plus dot 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 expectation of something, which would be 0, basically. So we end up with this, basically. And so we have m minus k plus 1 lots of exi minus the xj all squared xk minus the xj all squared, right? And it's also easy to see that property here, because if the xj parts were different, so if you look at it as, say, xj1, xj2, then we would have and they were different, then we'd have two independent terms, and then this would be 0 instead, but it's not, because these terms are the same, and we have m minus k plus 1 lots of the same terms, if you think of it intuitively. Like, I mean, I've sort of jumped a few steps here, but yeah, okay, keep going. So that's basically our covariance. Now, likewise for k greater than I. Actually, I should have explained that before. I had I less than k. Now, for k greater than I, it's just replace the subscripts, the letters, basically. So we have m minus I plus 1 exk. So it's the same sort of thing, basically. So next line. Okay, so now we're going to evaluate the whole thing, the whole of that covariance section. So basically, what we're going to do is we're going to split up the covariance parts in terms of k being bigger than I and k being less than I. So basically, so essentially, in this first term of the covariances, we have actually k greater than I. K will always be bigger than I, right? And the second term, we have k less than I, right? Now, because for the first term k has to be bigger than I, I've actually set limits of the sum for I to be less than, or the maximum limit of the sum of I to be less than that is what k, because otherwise that would set I and k to be equal at some point, which can't happen. Similarly, for the second term, I've set the limits for the k summation involving k to be less than that of I, because otherwise it'd be the same sort of situation. We would have if k was m minus 1, then if k went to n minus 1, we would probably have I think we would have a situation where I and k are the same, which can't happen. So yeah, basically, now these two terms are actually, they give the exact same result, right? So we end up with this. So it's just twice that, basically, because they're actually symmetrical. They give the same result. They're symmetrical. I should have actually put it in brackets in the second line, because it should be 1 on n squared, n minus 1 squared, all in brackets. But sorry. Okay, my computer isn't screwing up. Well, it could be. Okay, so next, basically, we've taken what we found in the previous slide, the covariance, and we just inserted in there. So, and this is what we obtain. And summing, when we take double sum of m minus k plus 1, because our expectation is just basically like constants is at the front, at the back. We get n minus 2, n minus 9, and 3n squared, n minus 1. Hopefully that's correct. Okay, next we're going to be evaluating 1 on n squared, n minus 1 squared. So this section here. So this is basically the first bit. This is going to be equal to 1 on n squared. So basically it's the same sort of idea, right? We have a variance of sum, so we put the variance inside the sum. We're going to have n minus I plus 1 lots of variances, or sums of variances. And then we're going to have like this covariance section where we have n by I plus 1 minus, we have like, yeah, so it's a similar sort of idea. And I'm going to set Rij equal to xi minus xj just because it makes it easier to fit in everything. But I've actually included the actual values in most of the sections just to avoid confusion. So we have a look at the covariance of Rij squared, Rk squared is going to equal. So we have n minus I, so because j can't equal I, we're going to have n minus I minus 2 lots of expectations, right? And also noting with the covariance, the expectation of Ri squared is 0, so that's why we have this exi minus xxi squared xi minus xk squared, right? And also next section, basically we have no j terms to sum, so we can just write this as n minus I minus 1. And the computer is screwing up. Okay, so now we end up with this. And basically what I've done is I've added the extra summation on the very front of the entire variance bit, and I've summed it. I've summed n minus I minus 1, n minus I minus 2. So we end up with 3n minus 2, n minus 2, 3n, n minus 1, and then, yeah, it's very straightforward. So next we have this. We have the variance of xi minus xi squared. It's going to be that. And now we have that. So we have, yeah, and everything inside the summation sums to n minus 2, 2n squared, n minus 1. So hopefully this is correct. Now we can rewrite the variance of s squared as follows. So we end up with this. And noting those two last factors, erij squared, rik squared, and erij squared, kj are actually the same. So you can actually pair them together. So now we hope that this will somehow, we hope that we can manipulate this into this. So by expressing xi minus xj as in terms of mu, basically. So we hope we can manipulate it into this form. That's assuming that my logic's correct. If it is, then we can. If it isn't, then we can't. Or either that I've made a mistake somewhere. So yeah. Next part. So show under the assumption of normality, the kurtosis is 3, and establish that in this case, the estimate of the form of as squared with minimum mean square error is n minus 1 s squared divided by n plus 1. So let's start with the kurtosis first. So to find the kurtosis, basically, we're figuring out the expectation of x minus mu on sigma to the 4th. So we're going to start by letting z equal x minus mu on sigma, where z becomes normally distributed because x is normally distributed, and we're doing a normal transformation, a standard normal transformation, basically. And actually, so I'm confused, messing up again. So this implies kappa equals ez to the fourth, and you can actually prove this. It's not actually obvious because like it doesn't actually necessarily this doesn't work in every case, I don't think, but in this case it does work, I'm pretty sure. So next, so by expanding the Taylor polynomial of mzt equals e equals the excitation. So we have our moment generating function about t equals 0. It can also be shown that ez to the fourth equals mz, or the fourth derivative of our moment generating function. So this is just basic. You can prove this, but this is something that you should just know. Okay. So basically, what we're going to do is we're just going to find our moment generating function, which is just the expectation of EZT. I mean, e to the power TZ, right? And we end up with e to t squared on 2, and then we just differentiate it, and then we take the value of 0. So we end up with this. Oops, what happened there? Okay, that was weird. It's because my screen's messing up and the frames aren't disappearing, which is very odd. So it can also be shown that by taking the fourth derivative, we get that, and we set to 0, we get 3. Right, and you see what's happening here. My screen's screwing up. It's really messing up. So we have z. Let's pause it.